So today we're going to continue talking about functions, and I'm going to talk about another property or descriptor that we can have for functions. That description or property is called continuity. And to do a thorough job of describing what I mean by continuous or continuity, we need to use calculus, which is beyond the scope of this class. So I'm going to give you kind of a informal definition that'll be good enough for us to use. It's kind of like you know it when you see it kind of thing. But it can't be really technical without the calculus, which hopefully you'll see next year to some extent or another. So let's start with this informal definition. We say that a function, and that function I'll refer to as f of x, is continuous on a given interval if that function doesn't appear to break at any point on the interval. So basically, any part of the graph you can draw without having to pick up your pencil, that part of the graph is continuous. Okay with that idea? So if we think about it from like just drawing the picture, if you can draw some part of the graph without having to pick up your pencil, that part is continuous. If you have to then pick up your pencil, that's basically like a discontinuity. Each time you have to pick up that pencil in order to draw the graph. Now that's a pretty wishy-washy informal definition, but it's certainly good enough for us to get some intuition about what do we mean by continuous and not continuous without having to use any calculus. So when we talk about continuity, what we're mostly interested in then is places where the function fails to be continuous. We call those places discontinuities. And there's three main types of discontinuity that we'll talk about here. God bless you. Does anybody remember any of these? We've seen a few of them last year. Yeah? Okay. So the holes in the graph we called a removable discontinuity, but that is absolutely one of them. Yep. There's another one that we talked about a lot last year, even more than the removables. Good. Vertical asymptotes are a type of discontinuity. We call those an infinite discontinuity. And then there's a third kind that we haven't talked about called a jump discontinuity. Okay. So let's just look at some examples of some pictures of things that are each one of these types, just to build up a little intuition. So, for example, if I have y equals x squared minus 4x over x plus 2, the graph of this is going to look like a straight line with a hole in the graph oops, that's in the wrong spot. Let's just do that. That'll fix it. And that would be at the 0.24. Again, I did that in my head. It would not be an expectation that you're able to like instantly do that in your heads. It's just me giving an example. So this is a situation where we have a removable discontinuity. So for removable discontinuity, the graph could have just a hole in it like this, or that point could just be moved like to another location. So both of those count as removable discontinuities, whether that point is purely undefined or if that point is just not on the line where it should be. You know what I mean? There's a hole, but instead of like that point just being empty and gone, it's just been moved somewhere else where it's no longer connected with the rest of the graph. So either one of those two situations are removable discontinuities. Everybody okay with that idea? Okay. Let's say we have something like this. So this graph would look like this. So the vertical asymptote there we call an infinite discontinuity, because if we look at the end behavior as x approaches, in this case, positive 2, we have y approaching either positive or negative infinity in this case. If we go from the left, y approaches negative infinity. We ride here this direction, it goes to negative infinity. Or if we approach from the right, it goes to positive infinity. And we could certainly have a situation where, you know, it goes to, both arrows go to the same infinity. So say we had just the absolute value of the above graph. So that one would look like this, where both of the arrows are going to positive infinity. Either one is still an infinite discontinuity, whether the arrows point in the same direction or opposite directions at that asymptote. And obviously you can have multiple infinite discontinuity in the same graph. We saw examples of that in Algebra 3-4 last year. There are lots of things that we graphed that had multiple vertical asymptotes on them. Everybody feel okay there? And the last one, these guys were, those were infinite discontinuities. And the last one is the jump discontinuity. I'm not going to write an example of a function for this, mostly because to do this I really need to use a piecewise function. We haven't talked about what that is yet. So rather than drawing out the notation for it, I'm just going to draw a picture of kind of what it looks like, because the equation, the function that I'd have to write is not something that we've seen before, so it's kind of without any context to us. But you could write an equation for this, and it's not so difficult, but you know, we just haven't seen it yet, and it's more than I want to get into for this example, right? Like, we don't need a function to get an idea of what a jump discontinuity looks like. So you'll notice that this jump discontinuity is a pretty accurate description, right? You're just going along and the graph jumps up to a new and starts from a new spot. So if you notice this section here, the endpoint is solid and the starting point of the next section is open. That's not on accident. Could both of these points be solid? Why not? Well, it still would be a jump. It wouldn't be a function, though, right? If both of those points were filled, this would fail a vertical line test, right? Everybody agree with that? Yeah. So Miguel asked, could both of them be blank? Yes. Yes, they could. Would still be a function, right? Nothing fails a vertical line test if they're both open, but they can't both be closed. And still be a function. I guess if you're talking about relations, you could have them both filled, but not really something we're interested in this course. Does everybody feel okay about whether these things are infinite discontinuity, jump discontinuity, removable discontinuity? Okay. So let's just look at a couple of examples that we'll graph ourselves. I'm going to probably graph these in Graphmatica because it does a little bit of a neater job than maybe the graphing calculator simulator does. But if you want to graph this stuff that we're going to look at the examples from on your graphing calculator as well, you're more than welcome to do this. So the first one I'm going to graph is y equals 2 divided by x squared minus 4. So I typed my function right on up here. So if I graph this, what do we see? Some weird things going on. Valerie? There's an asymptote at 2 and negative 2, or you could say there's infinite discontinuity at 2 and negative 2. If you wanted to talk about this in terms of continuity, we could talk about where the graph is continuous. So we could say from negative infinity to negative 2, it's continuous. And then from negative 2 to positive 2, it's continuous. And then from positive 2 to positive infinity, it's continuous. Right? Because I can draw this section without picking up my pencil. I could draw this section without picking up my pencil. And then I could draw this section without picking up my pencil. So depending on what you're being asked, it's basically the same answer, just you have to make sure you're answering the question, right? Whether you're describing discontinuities where those are, or continuities where the graph is continuous, but it's, two sides of the same coin. Does that make sense to everyone? Okay. Let's look at another one. So let's say we have y equals x squared plus x minus 6 over x plus 3. See on that with that color on that background. Is white a little bit better? I think first period decided white was going to be the best color for this to see in the room. So take a look here and be careful. Do we see anything going on here, Ben? Yeah, we have this little hole right here at when x is -3. What do we call this one? Removable discontinuity. So again, we could say that we might say there's a removable discontinuity at -3, or if we wanted to, we could describe where the graph is continuous at. In this case, we'd say it's continuous from -infinity to -3, and then from -3 to +infinity. So you could, again, depending on what kind of question you were asked, you could describe where the graph is continuous or where it's discontinuous. They're ostensibly kind of the same answer. It's just, or the same information, just two different questions, right? Okay. One more example here. So let's say we want to graph y equals x cubed minus 2x squared plus 3. Probably should make this white. It'll be easier for you guys to see. X cubed minus 2x squared plus 3. Yeah, you're welcome. What does this look like? Kind of a trick question. Yeah, there's no discontinuity here, right? That's what we were hoping for you to notice. So again, if you were talking about where this is continuous, it's continuous everywhere. In general, if you look at that function, x cubed minus 2x squared plus 3, what kind of function is that? Polynomial. Guess what we can say about all polynomial functions? They're everywhere continuous. All polynomials are everywhere continuous, which hopefully shouldn't come as a surprise, right? You've graphed a lot of polynomial functions in your time, whether they were linear functions or quadratic functions, or just typing in the graphs for big polynomials when we solved polynomials last year. In all those situations, you never saw any kind of discontinuity when you were graphing. And it is true that all of these polynomials are everywhere continuous. So you can store that little fact for later. Yes, absolutely. So the next thing we want to talk about in section 4 is increasing, decreasing, and extrema. So here we'll start with a technical definition. We don't need anything fancy to define what we mean by increasing or decreasing. So we say a function that we'll refer to as f is increasing. And I'm going to actually define 3 things inside of this definition. I'm just going to do a little bit of color coding so I don't have to write down all of these different definitions that are mostly the exact same words. On a given interval, if, maybe comma after the if, for any 2 points on the interval, a positive change in x results in a positive a negative or no change for f of x. Is everybody clear how to read this definition as 3 separate things? I tried to color code it in a way that would be easy to see rather than writing the same definition like basically 3 times. How clever and thrifty is your teacher that just doesn't want to write down a bunch of different mumbo jumbo? Yeah. Like all good mathematicians, I am lazy. I would rather be a little bit clever and write a lot less than just do the obvious thing and write a lot. You know what I mean? We like cooking up symbols and little notations, little tricks to avoid having to write a lot of stuff down. So what is this really saying? It's saying that if I take some section of my graph, and if I pick any 2 points from that section and calculate the slope between those 2 points, if the slope is always positive, the graph is increasing. If the slope is always negative, it's decreasing. And if the slope is always 0, it's constant. Now, I want to be clear that we're not actually calculating the slope of that function, because a lot of these functions are curves that don't really have slopes because they're not straight lines. But if I pick 2 points on a section that's increasing and calculate the slope between those 2 points, not the slope of the function, it would be positive, negative, or 0. You guys get what I mean? Let's draw a picture just to make sure we're clear. So let's say we have a function that looks like this. Everybody okay with that? If I picked, or hopefully you can see that this section is increasing. Everybody agree with that? That if you imagine you're a little man walking along the graph, at that point you'd be walking uphill, you're increasing. So if I picked these 2 points and calculated the slope between these 2 points, that slope would be positive. That's not the slope of the function between these 2 points, because that function is curved. It could be doing all kinds of things in between there, where the slope is changing, right? But all we're doing is looking for a measurement to check whether we're increasing or decreasing, or a really tight technical definition to indicate whether we're increasing or decreasing or constant. Is everybody okay with that idea? Let's look at a more interesting picture here. I don't know about more interesting, but I can do a little bit more with it. So Miguel says already that it's got all three. I agree with that. So let's just, before we write down the intervals specifically, let's just kind of look at the graph and label the parts that are increasing, decreasing, and constant, since he says there's all three. Where is the increasing part? Yeah, so the first part, negative infinity to 4. Where is the constant part? Negative 4 to 3, that middle part. And where is the decreasing part? 3 to positive infinity. Yep. So this is the increasing, that is the constant, and this is the decreasing. Everybody agree with that? Notice what parts I didn't circle. Yeah, I didn't circle these spots. Why am I not circling these? Because those are the transitions between increasing, constant, and decreasing. Any of those transition points should not be included in the intervals of increasing and decreasing or constant. Everybody okay with that? All right, so let's write this down. My increasing are the set of x's from negative infinity to negative 4. Everybody agree with that? My constant are the set of x's from negative 4 to negative 3. And my decreasing is the set of x's from 3 to positive infinity. Lindsay. So when we're describing an interval, we're talking about the x coordinates. So we're talking about negative 4 to positive 3 for the constant part. Oh, I'm sorry. I thought you said 4 to 4 or something. I'm just dumb. Yes. That should be a positive 3. Thank you. Lindsay pointed out that I wrote a negative there, and I just didn't understand what she was trying to tell me. Next time, be more clear that you're just talking about that I made a mistake. Be like, I think your interval of constant is wrong. That sounded more like I don't understand rather than I think you made a mistake. That's why I was so confused. Well, it's okay to question it. It's like, did you make a mistake is not a bad question to ask. You can certainly frame things that way. That's okay. Val. Of course. Do we feel okay about this one? Let's look at another example here. So let's say we had this function. So if I'm going to try to determine where it's increasing, decreasing, and constant, what would be the first thing I'd want to do? Graph it. Yep, that's exactly what I would do first. So again, you can do this on your own graphing calculator, or you can just watch what I'm doing here on Graphmatica. It's just easier for me to embed this stuff inside of OneNote, and it goes a little bit faster, and the pictures I think are better for later viewing with this software, but we'll certainly take some time if you want at some point later on and go through how to do these things on your calculator if you're not quite sure. Oh, I think we said the white was the best color for these, right? Now maybe let's zoom this a little bit, or at least get a little bit different grid range. It's a little bit better. Okay. And put that in here. Okay. So, increasing, decreasing, and constant. How many intervals of increasing do you see? 2. The first one is? Yeah, the very beginning piece, right? Everybody can see that? Where's the second one at? Yeah, like the first half of this parabola. Everybody good with that? How many decreasing sections do you see? 2. The first one is the other half of the parabola, and the other one is the right-hand piece. What do you notice? No constant part. Okay. So if I'm going to do the sections that are increasing, I have negative infinity up to, it looks like there's an asymptote at -3. And then I use the union symbol to connect my next interval, which begins at -3 and goes to 0. Oops. Keep forgetting that little element out. And then decreasing. We'll start at 0, go to +3. And then again, I use the union symbol to attach the next interval. And then I go from 3 to positive infinity. Right. So again, the transitions where we're changing from increasing to decreasing are not included. So in this case, Miguel points out that 0 is the transition where it changes from increasing to decreasing, so that shouldn't be included in either one of them, so we're going to use parentheses here. Question for you guys. I went from -infinity to -3 and then -3 to 0. Could I just write it this way? Is that okay? Why can't I do that? And why is that a problem, though? Yeah, exactly. -3 is an asymptote. It's not part of the domain. The graph never crosses -3. That shouldn't be included in any of these intervals. So this one is bad. That's a frowny face. So let's talk then about Extrema. So I'll do a multiple definition for this as well. So we say a maxima or minima of a function f is a value f of c that is greater or less than or equal to all the other range values of f on some interval containing c. And maybe we should say some open interval. By open, I mean the interval has parentheses at both ends of it. This definition doesn't quite work if you allow for closed intervals. C is just some x value. C is the location, basically, of that maxima or minima. So just to help with a little bit of the notation, so let's say this is our f. We can see that point there is a maximum, because if I consider the interval there that I've shown on the x-axis, it contains the point C, and the y-coordinate for that C, f of C, is the highest y-coordinate inside of that interval, right? Everybody can see that? So that's a maximum. Just to help out with some of the notation there, right? Hi, JJ. Now, there's actually two kinds of maxima and minima. We have local, and then we have global. Sometimes people say absolute instead of global. They mean the same thing. So, a local maximum is like what we've drawn in the example above. However, that maximum is not a global maximum. If I consider say, the interval from here to here, f of c is no longer the highest y value. We have stuff over on that edge that is higher. Can everybody see that? In this case, we have one local and we have no global. Because no matter if you pick the interval to be the entire x-axis, there's always one point higher than the point you picked, right? Because we have an arrow that's pointing up. Does that make sense to you guys? So, sure. Yeah, let's look at an example where we have both a local and a global. So this function has two maxima. Everybody agree with that? We have this here, that's a local. This one here, that's a global. We'll write max after that. Everybody agree with that? Now let's look at the minima. How many minima do we see? One. Is it local or global? Local. And it's local because we have arrows pointing down, so there's always going to be some point lower than that one, which makes it just a local. Okay. No. Let me show you an example counter to that, okay? Because that's a good question. So she says if there's two maximum, is one of them always going to be a global? So what if we have this? So this is a local max. This one is higher. It's still a local max because there's still stuff higher than that. Now, yes, Michael.
So I think do like the local max, except like the safety policy points to global max.
Correct. Yeah, if the end behaviors are not pointing up,
Then it's all working on all of it.
yes, basically. Yeah. Do we feel like we got the hang of that vocab between the local and globals? Taylor, you feel better about that? Okay. That was a good question, though. Like, again, it's easy to, to think, oh, okay. And then you see another counterexample, and you're like, okay, not going to be that simple. But in general, if you look at the picture, it's easy to tell when you have a local and when you have a global to determine, like, how many they're going to be or, like, which one is which. You just have to kind of look at it. The one thing I will say is in the situation where you have, like, one end of your graph pointing down and one end of your graph pointing up, you can have no globals, right? You can have lots of locals if you have one end down and one end up, but you can have no global because there's always going to be a point lower or higher because you have one arrow going down and then one arrow going up. Kayla, do you like that? So that's something, right? We can at least find a situation where there's no globals. Okay. If we wanted to find the locations of these maxima or minima, and all we're given is the equation, how do we do this? Until you get to calculus, it ain't going to be by hand. Val? We're going to graph it and use functions on our calculator. Yeah, that's exactly right. So just to remind you of the functions that we're going to need. Oh boy, that can get bigger. Yeah. I'm going to have, just type this into the y equals menu. Everybody remembers how to do this, right? Okay. I know it's been a little bit, but like graphing a function is probably one of the first things you learned how to do with your calculator. And then if I hit graph, I know that since my RAM was just reset, my window is going to be appropriate, -10 to +10 in both directions. If I wanted to say find this point, this is a minimum, right? Everybody agree? In fact, it's a global minimum because it's the lowest of the lows. To find that, I can press second and trace. And which command do you suppose I want there? Minimum. So to use the minimum, the calculator is going to ask me a couple of questions. It's going to ask me first for a left bound. So what it wants me to do is move my cursor left of the minimum that I'm looking for. So right now I see my cursor flashing right there. I'm just going to use the left arrow to move my cursor until I can see that it's on the other side of that minimum. So I am now left of it. I'll press enter. It has changed its question now. It wants a right bound. So I'm just going to move my cursor somewhere where it's on the right side of that minimum. So now I'm right of that minimum. I'll press enter. And then it asks for a guess. Here's the thing with the guess. You don't have to move it to make a guess. Just press enter where it's at. It might take like a fraction of a second longer without an excellent guess, but it's less time than it'll take to move the thing. So this minimum, the C value is -2.242626, and the F of C is -9.653029. and the maximum command works similarly. Okay? For Tuesday, right? We meet next on Tuesday. I have an assignment for you posted to PowerSchool. I think it's like 13 to 18 from the homework. Let me just pull that up right quick. You can probably pause.